I will give a review of the complex algebra, and the reason why is this and why we need this, and I give you the reasons. From our standard form of plotting the root locus is 1 plus k times, let me put it in general description, it's something like this. Okay, so that is our standard form for this. So basically here the S, basically S meaning is the complex number, because usually we plot the S, we say the complex plane in terms of S. S can be any complex number, can be anything you name it. Okay, so here we see that basically LS is a function of the complex number. Okay, this can be polynomial in particular for our root locus topics. So from here you can see if here let me revise this thing. Basically this is minus k minus 1 over k. So here k is a constant. So that means for the root loci must satisfy these equations. Okay, so this is the standard form derived from our standard form. But right now, let us looking at these equations from the point of view of the complex algebra. We see what is this. On the left hand side, this one basically is functions. I would say a polynomial. Of complex number. Okay, and many complex numbers will get into here. And right hand side, this one is a constant. And actually, here I want to emphasize is a negative constant, because for our drawing, our standard form here, in our exercise, we're focusing on this range. Okay. So under this situation, this is a constant negative, and if we explain a number in the complex plane, usually we not only focus on the number's magnitude, but also we focus on the phase, which means the angle, right? If you remember the complex numbers analysis, here we can say, here, if this is a complex plane, okay, and here let me make out a few examples here. So if we have a number here, say this number is 3, positive 3, okay, that's easy. And here, if we have another number that is minus 2, okay, minus 2. For any real numbers, they lie on the horizontal axis. For example, here in any complex number, say we might have something here, and later I will point to this point. Basically, we might have a number here. This number have the real part, have the imaginary part as well. Okay. In particular, we look for a negative numbers here. For example, if we have a negative number minus 1 over k located here, we see for this number, it actually gives us two pieces of information. One is about the magnitude. Magnitude is equal to how much? Is equal to the distance we measure between the origin and this number. Basically, we just measure the distance. So that is given by 1 over k. In the meantime, what is the phase? The phase, later I will give a review. The phase, basically, we measure counterclockwise from this arrow to wherever the point there. So basically for this phase, equal to 180 degrees. Or in complex number, basic complex number is a system with the infinite numbers of the equivalent description. So basically we say this is 180 degrees, that can be also equivalent to 180 degrees plus additional 360. So that means we can say 800 degrees plus n times, I would say, L times 180 degrees, L times 360 degrees, right? And L can be any number, 0, 1, 2, 3, or can be negative, negative 1, negative 2, negative 3, etc. Be good? So here we have the pieces informations. So from here, we really want to solve for, in terms of the root locus, is we're looking for the collection of the S, and that will make this polynomial of complex numbers to satisfy these equations. And in a way, is this we have to satisfy the magnitude as well as the phase. Okay. So as long as we have the collection of the complex numbers making this satisfy the both, then that collection will give us the root locus. Okay. And all the rules, the systematic rules of drawing the root locus derive from this single equations here. Okay, so here that's the reason why we need a certain review on the complex algebra. And I will only give to you whatever the tools we're going to use. And by ignoring all the other, I would say, unnecessary tools, we won't be used. Okay, so here the review is the first one. We consider any two complex numbers. Say here S1 equal to A1 plus JB1, and S2 equal to A2 plus JB2. Okay. So from here we have, for example, here let me label it. So anything, any plane I'm going to draw in this chapter is we call the complex plane. If sometimes I didn't write these words, you should know we are working on the complex plane. Okay. So for example, here we have S1 point is here. Here is the real part, and here is in the imaginary axis. Okay. So that means once we label this one here, that means here the S1, and graphically this is A1 and this is B2, B1. So we, by conventions, we put the real numbers into the x-axis. We put the imaginary numbers into the vertical, which means y-axis. Okay, that's the graphical representations. And usually we like to borrow the concepts of the two-dimensional Cartesian coordinate systems to describe the location of a complex plane, a complex number on the plane. So that means here this we can also describe as A1 and B1. So using this notation is to borrow the Cartesian coordinate systems to label the plane. Okay? And with this one, then we can define the magnitude. The magnitude basically is to measure the distance between the point to the origin. Okay, so this one is called the magnitude. The magnitude, from the graphically here, you can say for S1 is magnitude. We're using notations. We're using the notation absolute value, that symbol, to denote the magnitude. Okay. So for this case, the magnitude basically, by definition, is the distance between the region to the location of the complex numbers. So from here, the graphically, you can pretty much easily tell that one basically is determined by the square root of the squares of the individual part, A1 squared plus B1 squared. So this is a real part square. This is the imaginary part square. Very straightforward. Okay. And then the phase basically is determined by the angle. By sign conventions, we measure counterclockwise as positive. So for this particular example here, S1 has a positive phase. Okay, by sign conventions, we define counterclockwise measurement as a positive angle. So for this case, what is this angle? So phase, that means is the angle, okay? So here we're using the notation using angle symbol, and we put the S1 here. That means basically we indicate that is the phase, okay? So for this case, we want to measure this angle. We're simply using trigonometry. Basically, that is arctangent and B1 over A1. We good? Okay. Then we have two numbers. Then we want to see and the relative information here. So for example here, we have, okay, so here S1 is here, okay. So for example here, we might have, say, I just arbitrarily put the S2 to here, okay. So right now we have S1 and S2, and both have the real part, the imaginary part somewhere defined it, okay, so that's the real axis, imaginary axis, okay. So here, if we do the algebra and say S1 minus S2, what this means, this one in algebra simply is looking for the difference of S1 and S2. Actually, we subtract S2 from S1, so that is an interpretation from algebra. Graphically, that representing is this. Again, graphically, we borrow the concept of the two-dimensional Cartesian coordinate systems. So if you wish, you can visualize S1 as a vector that is pointing from the origin to where it locates. Okay, right now I'm talking is to borrow the concept of the vectors in Cartesian points. So basically, this is a vector, this is another vector. This representing is the difference between two vectors. If you like, you can use this one. Okay, here I put the arrow to indicate that basically taking the difference, subtraction is S1 minus S2. On the other side, if I would say S2 minus S1, then basically you simply flick the arrow to the other directions. You good? Okay. The sense is important. So under these situations, the magnitude is S1 minus S2. Okay, and you can verify the magnitude of S1 minus S2 equal to the magnitude of S2 minus S1. Okay, doesn't matter which one the arrow is near, the magnitude is the same. Okay, so for this one, again, the magnitude is, again, the distance of the line we label here. So basically, this is the magnitude. If you can calculate, then that is the magnitude. That is the distance between the 2 points. So what is the distance between the 2 points? Again, here we can, using the geometry here. So this distance representing is A1 minus A2. Okay, and this distance is B1 minus B2. So from here, again, that magnitude simply is the real part square plus the imaginary part square. Okay, the phase, the angle S1 minus S2. Okay, and this is 90 degrees here. Again, this is the phase. Okay, we measure counterclockwise from the horizontal directions. So that is a phase, and that can be determined as arctangents B1 minus B2 and A1 minus A2. Okay. Good. Then we can look for the further information. So that is the first one, and this is the second point. So we started from a single number to the subtractions, and then the third one we consider is a polynomial. Say okay, if we have this one, then where as is the complex number. Okay, so basically this is a polynomial of complex number. This is another polynomial of the complex numbers. So basically the whole thing is we can calculate it can be a complex numbers here. So here for this case is the magnitude equal to L over S. S is the complex number. If we want to calculate, basically equivalent to is the magnitude of the numerator divided by the magnitude of the denominators here. Okay, and for this case, the face equal to L over S, and that one basically is the face of the numerators minus the face of the denominators here. And we can use a few examples to exercise. So for example, here the LS equal to 1 S plus 2. Okay, so for this case, say we put the S equal to sigma plus J omega, okay, the parametric expressions here. So basically here, then here L, these functions will be sigma plus J omega plus 2 over 1. Okay. So in this case, here we have the magnitude will be simply is equal to the magnitude of the numerator, that is easy, equal to 1. The magnitude of the denominators, we plug in the first property there, and real part square plus the imaginary part square and take the square root. Okay. The face angle, the face is equal to, again we plug into the first properties, numerator equal to 1, real number 1, so its face angle equal to 0 degrees, and minus the face angle of the denominators, and here that is omega and sigma plus 2. Be good? Then we can look at another example here. So say right now we look at here, for example, S minus 2 and S plus 2. Okay, so here again we let S equal to a parametric expressions of the complex number here. Okay, so in this case, this one will be equal to sigma minus 2 plus J omega. This is sigma plus 2 plus J omega. We simplify it. So therefore here the magnitude will be equal to square root sigma minus 2 square plus omega square, sigma plus 2 square plus omega square. Okay, and the face angle will be equal to arctangent numerator, that is omega minus 2 minus arctangent omega sigma plus 2. You good? Okay, we still apply this kind of the rules and getting more, get the more terms kind of writing here. Okay. example here. So right now we are considering the standard form of plotting the root locus like this. Okay, and for this case, right now the S shouldn't be arbitrary, but S must be satisfied. S must be the numbers, the complex numbers satisfy these equations. So that means under these situations, I wouldn't say S is arbitrary parametric like this. No, because they wouldn't be arbitrary. Okay. So for this case, let me rewrite. So that means QS and divided by PS will be equal to minus 1 over K. Okay. So for this case, we know this equation must satisfy is the magnitude is equal to 1 over K. Okay, its phase angle equal to 180 degrees minus 180 degrees plus L times 360. Right? So which means this implies is this the magnitude of QS divided by the magnitude of the PS equal to 1 over K. And the phase angle minus P must be equal to minus 180 degrees plus L and 360 degrees. And L can be the integers. Any arbitrary integers. Okay. So by solving the two criteria, then the solution for that S will be the part of our root loci, the other root locus. You good? Okay, so basically here I highlight this is our starting point of drawing the root locus. Okay, if you like, you can make a note here. This is our starting point of this. Okay, and the fourth one, usually we have the expressions. So say earlier in the first property, say we have S1, N1 plus B1. We have these expressions. Okay, so in that particular case, and I draw is like this. So this is the real part and imaginary part, and S is here. Okay, S1 is here. And in that case, we have the magnitude, and we have the phase angle, right? So basically, this is the magnitude S1, and this is the phase angle of S1. Back to the first portion, the first properties. Okay, so here if say let us pick up certain notation. So let me define this one as the sigma, and let me define this as theta. Okay. So if we have magnitude and phase angle be calculated, so usually we have another expressions of the complex numbers directly expressed in terms of the magnitude and phase, which is this. If you remember that one, J theta. Okay, so here we introduce a very particular notation. This notation only valid in the complex plane. This is a definition. Okay, this is not, well, we can prove it. This can be a derived quantity, but we don't have to. Okay, so basically here, if you wish, you can treat this as a definition. By definition, this determined is defined by this cosine theta plus J sine theta. Okay. So by definition, this one basically is meaning this. This is a single complex numbers, okay? And the complex number has the angle theta, the phase angle theta, and its magnitude equal to 1. Okay, and in terms of the second two-dimensional trigonometry, two-dimensional Cartesian coordinate system, basically this is cosine theta, and the vertical is sine theta. So basically, taking up is the real part, and then the imaginary part they lay out in the two dimensions. Somehow combined to our complex plane, this is the real part, and this is the imaginary part. So here we added up J here. Okay, so that's a definition if you like to trade it. Okay. So this is our new notations. So if you have this one, then we can have this. Okay. So therefore, with this one in mind, by definition, then we can calculate, say, as if we want to multiply s by n times. Okay. So if we want to multiply the s by n times, so we can use this very powerful definition. Basically, the formula we can calculate, but here I directly give you the result. Basically, is the real part multiplied by n times, and then in terms of the phase angle, added up n times. Okay. So basically, graphically, you should be able to draw this quickly. So once you have this information, you simply multiply the sigma by n times that given the magnitude, and then given this n theta, you simply add it up n times, then that the n theta will give the phase angle of this one. Okay. Okay, for this, I like to keep this portion because later we'll start with this one. So right now here, I just summarize the useful information for everyone. So now the fifth one, I want to give more graphical interpretations of the algebra, the complex algebra. So say, for example, consider as plus 2. Okay. And I would say consider transfer functions. We try to combine with our control concept into complex algebra. So here I would say transfer functions, okay? S plus 2 only. So usually we are familiar with transfer function is in this form, y over r equal to, for example, for this case, s plus 2, and in denominator is 1, okay? So in this case, from here you can see, here we have 0, which means the root of the numerator polynomial equal to minus 2, right? Okay, I simply plug in to combine the concept of control. So here we can plug in here. So here I want to give you what is really the graphical meaning of this operation here. So that is the real part, and this is in imaginary part here. So here we have a 0. Let me use the circle, and that is at minus 2. Okay, and again I combine these the convections of the symbols in control on the complex plane. So say S is an arbitrary complex number. For example, say S is here. Okay. So what means S minus S plus 2? S plus 2 actually is equal to S minus minus 2. So basically that indicating is using this arrow, using these vectors. So S plus 2 in algebra, that can be represented graphically, representing is the distance between the S and the 0 minus 2 there. Okay, good? Okay. So under these situations, and you might try is this. So for example, therefore, using this graphic, so the magnitude of S plus 2, so simply will be equal to Yeah, just this one. Okay, just yeah, nothing much. So let me label here. So this one, the distance is s plus 2. Okay, and this phase angle is the angle of s plus 2. Okay, so this is nothing. We can put the labels on the drawing. So similarly, if we consider a transfer function y over r equal to say s plus 2 here, okay? So for this case, basically this is a pole. Okay, so that means here we have the similar way. So for this case, this is a pole here, and minus 2, and then the arbitrary number s here. Okay, so again, this is the magnitude, and this is the phase angle. So for this case, here we can exercise the magnitude of these transfer functions. Basically, we can do this calculation is this one, s plus 2. So that means that is equal to 1 divided by s plus 2 per our properties there, the property 3. And the phase angle of y over r, basically from there plug in these properties, and that is the phase angle of the numerator minus the phase angle of the denominators here. And this one, the phase angle of 1 equal to 0 degrees, and this phase angle equal to arctangent, and basically given by this angle. Okay, so here I would say just leave it and s plus 2. So if you like, you can further detail these calculations. Okay, this angle basically is defined by this one. Good. Combine the two things together. I would say this is the 1, this is 2, and 3. I would say similar. So say if we have a transfer functions, for example, here we combine, say, as, let me make up one. So s plus b and s plus a. A, b are certain real numbers. Okay, so under these situations, we're going to calculate what is this magnitude. And this one will be easy. Again, we're plugging into that properties that can be simply is this s plus b and divided by s plus a, right? And its phase angle, the phase equal to s plus b minus s plus a. So that is the direct calculations per this kind of the properties. Graphically, that is more useful is here. So that is the real part and imaginary part here. Okay. So from here we have a 0 at s equal to minus b, and we have a pole at s equal to minus a. So let me label it. So for example, here we have a 0 at minus b here. And for example, here this pole is here minus a. Okay? And so say, for example, here we have the point here. How about this? I put the point here. Okay, so graphically, I'm going to show you the meaning of this one. So here we connecting this one representing this one, vector representing is s plus a vectors. This vector representing as s plus b vectors here. Okay, so in this way, this magnitude simply is a ratio between the magnitude of the green vector and red vectors here. Okay. And the angle, what is S plus B? S plus B is this angle here. Okay, so let me use color. So basically that corresponding is that color here. And S plus A, that is the angle corresponding to this. Right? So let me replace with the color here. Okay? So tell me for this example, the phase of the transfer function is positive or negative. By looking at the graphics here. Positive, right? So John, speak loud. So here this angle is larger than this one. Okay, so for this particular example, this is negative. You good? Okay, good. So that is the color.